In this section, we're going to learn about another kind of vector operation called the cross product. The cross product is similar to the dot product in that it's an operation between two vectors. But whereas the dot product was fairly simple, the cross product is a little bit complicated. So before we jump right into taking the cross product, we're first going to learn something else to help us stay organized. We're going to learn how to take the determinant. Now, if you've taken linear algebra, you probably know how to take determinants already. You probably know what they're for. In this class, we do not need to know what determinants are for. We just need to know how to take them. It will help us stay organized. Okay? So I'm going to start with a 2x2 matrix. Matrix is just a ordered list of numbers. So maybe I'll start with, let's do A, B, C, D. Let's learn the general formula. Okay? And then I can indicate that I want to take the determinant by these vertical lines. Okay? So this is a 2x2 matrix because I have 2 rows and 2 columns. And the vertical lines say I want to take the determinant. The determinant is going to give us a single value when we're done. Now for a 2x2 matrix like this, to take the determinant, I'm going to multiply these two. So that's A times D. And then I multiply these two, C times B. And I subtract. And that's all there is to it. That's a 2x2 determinant. Okay? So 1, 3, 5, 4. Take the 2x2 determinant. 1 times 4 is 4. I'll actually write it out. And then I go the other direction, 5 times 3. I subtract. 1 times 4 is 4. 5 times 3 is 15. 4 minus 15 is negative 11. Okay? So 2x2 determinants, nice and easy. Okay? 3x3 determinants are a little more complicated. So now let's look at a 3x3. And I don't want you to memorize the formula here. I want you to understand the basic idea. So we're going to take the 3x3 determinant by taking lots of 2x2 determinants. Okay? What we're going to do is we're going to expand along this first row, one element at a time. So I'm going to start, and maybe I'll color code it so you can kind of see where things are coming from. I'm going to start with A. I'm going to get rid of the row and column that A are in. Just mentally, most of the time we don't draw these lines. Okay? That leaves me with a 2x2. Take the 2x2 determinant. Okay? So that's E times I and H times F. So we're taking that 2x2 determinant just as usual. We got that by canceling the row and column A's in. And now we're going to multiply by that element that we're focusing on in the first row. Okay? I'm going to do this same thing with each element in that first row. So I did it with A. Now let's do it with B. Imagine canceling out the row and column. Again, we don't usually actually cancel out the row and column, but since I have an undo key, I can do it to show you. Okay? Usually we just imagine it though. Focus on the 2x2 that's left over. That's DI times GF, right? So DI, those two, and then GF, those two. Subtract them, and then multiply by that element in the first row. In this case, B. And we're going to do it one more time for the last element in the first row. So do it with C. Imagine canceling out the row and column. Focus on the 2x2 that you would have left. Okay, I'll get DH minus EG. So DH minus EG, and then multiply by that element in the first row we were focusing on. So that would be the C. Okay, and then we want to alternate signs. So plus, usually we don't actually write the plus, so no sign change there, minus, plus. Okay, that is how you take a 3 by 3 determinant. We could take a 4 by 4 determinant too, but we don't need it for this class. You do the same thing. If it's a 4 by 4, you'd expand along the first row, cancel out every row and column, but then you're left with a 3 by 3 every time you do that, right? And so you take a 3 by 3 determinant for every element in that first row. Again, we don't need to go past 3 by 3 in this class. We really need to focus on that 3 by 3 though for the purposes of this section. So let's take a look at an example. 1, 3, 0, let's do 2. 0, -1, 4, 1, 0, -3. Okay? So, expand along the first row. I'm going to take each element in the first row one at a time. Imagine canceling out the row and column it's in, and then take the 2 by 2 of what's left. Okay? So I get 3 minus 0. And maybe I'll write it out all the way just because it's our first time. -1 times -3 minus 4 times 0. And then multiply by that element that we expanded using. Okay? So multiply by that 1. Do the same thing for the next element. Okay? That leaves me with 0 times -3 minus 4 times 1. 0 times -3 minus 4 times 1. And I'm going to multiply by this number since that's the one I used to decide which row and column to cancel with. So multiply by 3. And then finally the 2 at the end. Cancel out the row and column with the 2 in it. Focus on what's left. I get 0 times 0 minus -1 times 1. 0 times 0 minus -1 times 1. And then multiply by that 2. Okay? And then alternate the signs, right? Plus, minus, plus. So that is my 3 by 3 determinant. All that's left now is a little bit of arithmetic. I get -1 times -3 is +3, minus 0 is +3 times 1 is 3. 0 minus 4 is -4 times 3 is -12, but there's already a negative in front, so it becomes +12. 0 times 0 is 0. -1 times 1 is -1. 0 minus -1 is +1. Times 2 is +2. And so the 3 by 3 determinant of this matrix is 3 plus 12 plus 2, that's 17. All right, so let's put aside determinants for a little bit. The main point of this section is when we are in three-dimensional space and we have two vectors in that space, we notice something. Okay, so let's say we have two vectors, u and v. And it turns out that if you're in three-dimensional space, there is a unique direction that you can pick that would be orthogonal to both vectors at the same time. So this direction would be orthogonal to v, and at the same time orthogonal to u. Meets both vectors at a 90-degree angle. Our goal is going to be to find a representative vector in this direction. Okay? Let's call it W. That's what we want to do in this section. Now I want to emphasize that finding this vector, it really is something unique to three-dimensional space. In two-dimensional space, I just can't do it. Okay, if I'm in two-dimensional space and I have two vectors, U and V, there is no one vector that is orthogonal to both. The direction that would be orthogonal to both is coming straight out of the screen, right? So I can't do it in two dimensions. In higher dimensions, I can find a vector orthogonal to both U and V, but the problem is there's too many choices. There's an infinite number of directions to choose from, okay? Whereas here, I have one direction to choose from, okay? And so that's why we're focusing on R3, why we're focusing on 3 space. All right. So how do we go about finding W? Okay, how do we go about finding a vector that is orthogonal to both U and V? Well, what do we know? We know that when two vectors are orthogonal, their dot product is 0. So that means vector U dotted with vector W should give me 0 because they're orthogonal. Same thing for V. Vector V dotted with vector W is going to give me 0. Okay, so what does that mean? Let's translate that into its individual components. Let's actually take the dot product. So I'll just multiply corresponding components. So that'd be U1 times W1 plus U2 times W2 plus U3 times W3 equals 0. And then same thing for the second equation. Taking the dot product, multiplying the corresponding components, and then adding them together, I get V1 times W1 plus V2 times W2 plus V3 times W3 equals 0. And so I get a system of equations. Now, note how many variables I have in this system, how many unknowns there are. W1, W2, W3. These are my unknowns, okay? The U's and the V's, I'm assuming I know. I know vector U, I know vector V. What I want to know is a vector orthogonal to both of those vectors. So I have 3 unknowns, W1, W2, W3, but only 2 equations. Generally, in order to find a unique solution to a system of equations, I need at least the same number of equations as I have variables. Because I have fewer equations than I have variables, if this system has a solution, it won't be a unique solution. There will be more than one possible solution. And if we think about it, that actually makes sense, right? Because vector W, as I've drawn it, would certainly be a solution. It would be orthogonal to both U and V. But there are also lots of other vectors that would be orthogonal to U or V. All I got to do is change the length. Right? I could even go in the opposite direction. It'd still be orthogonal. But they're all essentially in the same direction. They're all scalar multiples of each other. Okay? So I shouldn't be surprised that there are lots of possible solutions. What we want to do is we want to find one representative solution. We want to find one possible choice for W. Then every other possible choice would just be a scalar multiple of that first choice. Okay? So how do I go about doing this? Well, let's eliminate one of the variables. I'm going to multiply the first equation by negative V1 on both sides, and the second equation by U1 on both sides. And that way, the first term of both equations will be the same, just with opposite signs. And so I could add the equations and eliminate that first variable W1. Okay, so I'd get for my first equation, it would become U1 V1 W1 plus minus negative. I'm multiplying by a negative V1, right? So negative U1 V1 W1 minus u2 v1 w2 minus u3 v1 w3. And on the right-hand side, anything times 0 is 0. And then the second equation, very similar. I get u1 v1 w1 plus u1 v2 w2 plus u1 v3 w3 equals 0. Okay? And now I can add these two equations together and one of my variables will eliminate. Okay? Specifically, negative u1 v1 w1 plus positive u1 v1 w1, that goes away. And so now if I add these equations, I'll get a new equation without that variable w1. So if I add these up, they'll have the common variable w2, and the coefficient will be u1 v2 minus u2 v1 w2 plus, and then add these guys up, that would be u1 v3 minus u3 v1 w3 equals 0. So notice we've reduced the number of equations, but we've also reduced the number of variables, right? Lower complexity. Okay, but we still have only one equation, but two variables, all right? Now remember, we just need one solution to this. As long as we could find one solution to this, we know that all other solutions are just scalar multiples. So if I can pick a W2 and a W3 that will make this work, I have a solution, right? And then I can figure out the W1 that corresponds to it. So the easiest way we could see that this will work is if I make W2, so let me write the equation, so I get U1 V2 minus U2 V1. What I'm going to do with W2, I'm going to turn it into the negative of this. Okay? So U1 V3 minus, here, let me do it this way. Negative U1 V3 minus U3 V1. That's going to be my W2. And then I'll turn W3, I'll choose W3 to be the negative of this. And I do that because I notice it's a real easy solution to notice. Okay, U1 V2, I'm sorry, not the negative, the positive. Just keep it the same, minus U2 V1 equals 0. And let me just kind of write what I'm doing here. So if I have 2x plus 8y equals 0, well, one way I can find an xy that would make that work would be just to make sure that these have the same number, just opposite signs. So I could do 2 times, and so if I pick this number, but negative, and then over here on the other side, I pick y to be this number, but positive. Okay, do you see how I end up with the same number, just opposite signs? So I just pick this to be that, and that to be that, and I just make one of them a different sign. That's what I'm doing here. Okay, I'm choosing this to be this, and this to be this, and that way I know they'll have the same magnitude, and then I just throw in a negative somewhere. Okay? So that checks out. That works. So far so good. I've chosen W2 to be negative U1 V3 minus U3 V1. And I've chosen W3 to be U1 V2 minus U2 V1. Okay, now let's plug back into one of our original equations. Okay, way back up here, and I can figure out what W1 would be. All right, so let's plug into this first equation. That first equation was U1 W1 plus u2 w2 plus u3 w3 equals 0. Plug these guys in. u1 w1 plus u2 times w2, which I am choosing to be negative u1 v3 minus u3 v1 plus u3 times w3, which I've chosen to be u1 v2 minus u2 v1 equals 0. Okay, now just solve for w1. Okay, I'm going to go ahead and distribute this through, and I'm going to get negative u1, u2, u3 minus u2, u3, v1. And then same thing here, distribute in. Oh, and this one should be a plus, right? Double negative. There we go. Here I get, distributing that u3 in, u1, u3, v2 minus u2, u3, v1 equals 0. Now right away I notice u2, u3, v1, negative u2, u3, v1, they go away. Okay? I have u1, w1, and I'm going to move the other two terms to the other side. So I'm going to move this over. So I get u1, u2, u3. Sorry, that should be v3. And move this over to the other side of the equation. That's negative u1, u3, v2. And finally get the w1 by itself. Divide both sides by u1. Okay, that means all these u1s will cancel. And I'll get u2, v3 minus u3, v2. And so that gives me a w1 also. And so W, all said and done, is u2 v3 minus u3 v2. That's the first component right there. And then up here, we have our second component, negative u1 v3 minus u3 v1. So negative u1 v3 minus u3 v1. And then the third component, my w3, right here, u1 v2 minus u2 v1. u1 v2 minus u2 v1. Okay? This is a vector that would be orthogonal to these two vectors, whatever u and v is. Okay, that tells us a vector that's orthogonal to those two vectors. Okay, this is what we are going to define as the cross product of vectors u and v. So let u and v be vectors in R3. Again, this cross product only is properly defined for three-dimensional vectors. Then the cross product of u and v is, and we give it a special notation, u cross v. Okay, and this is how we define it. u2 v3 minus u3 v2, comma, negative u1 v3 minus u3 v1, comma, u1 v2 minus u2 v1. Furthermore, and here's the big deal, why we care about this, why we're doing this, because this doesn't look like a lot of fun to do, right? Furthermore, this cross product, u cross v, the resultant vector, is orthogonal to both u and v. Okay? Now, if you're on top of things, you may have a couple questions. One of them is, remember that this system of equations up here, it had more than one possible solution. The W we found here was one possible solution. This cross product is one possible vector that would be orthogonal to both u and v. But any scalar multiple of this vector would also be orthogonal to both u and v. It would also meet both those vectors at a right angle. So why did we pick this one over any other? Well, this one was very convenient to find based on the equations, but it turns out there's some really nice properties that this particular orthogonal vector has. And so that's why we choose this one. You'll see in a little bit those nice properties. Okay, so I know what you're thinking. This cross product thing, it is hideous. Do we really have to remember this nasty formula? Well, yes, but it turns out there is an easy way to remember this. Okay, and to see it, let's rewrite the cross product in terms of the standard unit vectors, in terms of ijk, instead of in component form like we have it here. Okay. In terms of the standard unit vectors, that we get that the cross product of u and v is equal to the first component u2 v3 minus u3 v2 times vector I minus u1 v3 minus u3 v1 times vector j plus the third component u1 v2 minus u2 v1 times vector k. Now as you're looking at this, in this form, it may dawn on you that this form looks familiar. This is exactly the kind of structure we have when we take a 3×3 determinant. Okay? This is equal to a 3×3 determinant with the first row being ijk, the second row being the components of u, the first vector, u1, u2, and u3, and the third row being the components of v, the second vector. And this gives us a way to be able to take the cross product without having to memorize this pretty complicated formula. You just have to remember it is the determinant where the first row are the standard unit vectors, ijk. The second row are the components of the first vector, and the third row in the matrix is the components of the second vector in the cross product. All right? Now, I do need to just say that this isn't a true determinant. This isn't a true matrix because the components of a matrix should be numbers. U1, V2, those are numbers. That's great. But I, J, and K are vectors. So this isn't a true determinant. It's more of a mnemonic device to help us remember the form of the cross product. Okay? So this is a mnemonic device, not a true determinant. But it's very useful for our purposes. So let's do an example. Find a vector in three-dimensional space orthogonal to both vector A, which we'll define as 2, 1, negative 3, and vector B, which is 0, 3, 2. Okay? So both of these vectors are in space. We want to find a vector orthogonal to both of them, and that's exactly what the cross product does. It gives us a vector orthogonal to two other vectors. Okay? So if I find A cross B, then the resultant vector will be orthogonal to both of these original vectors. Okay? All right, so how do I take the cross product? Well, we're going to use the mnemonic device. Okay, when we take a cross product, first row are the standard unit vectors I, j, k. Second row is the first vector. The order is important here, as you will see. Okay, first vector is the next row in the matrix. Okay, so 2, 1, negative 3. And the last row is the second vector in the cross product. So 0, 3, 2. All right, so now we take the determinant. So imagine canceling out row and column. I get 2 minus negative 9. So 2 minus negative 9, I. Multiply by that, right? I. Look at the next component, the next element of the row. I'll get 4 minus 0. So 4 minus 0 times j. And finally, the last component in the row, I get 6 minus 0 times k. Alternate signs, plus, minus, plus, and I have my vector written in terms of the standard unit vectors. 2 minus negative 9 is 11. So I get 11i minus 4j plus 6k. Or I can write this, if you choose to write it in component form, 11, negative 4, 6. Both of these are acceptable answers. And so this vector, 11, negative 4, 6, is a vector that is orthogonal to both vector A and vector B in three-dimensional space. I would like to take two very simple cross products just to show you the difference. I want to do I cross j first, and then I want to compare that to j cross I. Okay. Now here I and j are, of course, the standard unit vectors, right? So in 3 dimensions, I is 1, 0, 0, and j is 0, 1, 0. Now if you think about it, you could probably give me a good guess of what I cross j will be. So if you want to, you can. So let's take our cross product. So first vector is the components go in the second row here. And the second vector in the cross product, the components go in this row here. So if I take the cross product, I get 0 minus 0, I. 0 minus 0, I. And then j, I get 0 minus 0, j. And then finally k, I get 1 minus 0k. and then alternate signs, positive, negative, positive. Now, of course, 0 minus 0i, that's just 0. 0 minus 0j, that's just 0. So the only non-zero component I have here is this one here, which is 1 minus 0k, or just k, which, you know, not surprising if you were to think about it, right? In 3 dimensions, x, y, z, the unit vector in this direction is I. The unit vector in this direction is j. And so it's pretty easy to see that the unit vector that would be orthogonal to both of them might be pointing this direction. It's k, right? Orthogonal to both I and j. Okay, so great. I mean, that's what we expected, okay? But what happens if I swap the order? Okay, so if I do j cross I, that's 0, 1, 0, cross 1, 0, 0. Set it up in a matrix. I could take the determinant. Remember, first vector goes first, so 0, 1, 0 would be the first row of terms that I put here. Okay, and then 1, 0, 0 would be the last row. And I get 0 minus 0i. And then for j, 0 minus 0j. And then k, 0 minus 1 times vector k. Plus, minus, plus. These are just 0. So all I'm left with is 0 minus 1k, or negative k. All right? Now what do we notice? I cross j gave me vector k, but j cross I gave me vector negative k, which means the vectors are not commutative. The operation, the cross product, is not commutative. I cross j is not the same as j cross I, and generally u cross v and v cross u are not going to be the same thing. They're not going to give you the same vector. So you might ask, well, how do we know which direction we're going to get? Because this negative k, it's still orthogonal to both I and j, but now it's pointing the opposite direction, isn't it? Pointing this way. Negative k. Still orthogonal to vectors I and j. But pointing the opposite direction. So how do we know when it's going to point up versus when it's going to point down? So there's a simple rule for this. It's called the right-hand rule. All right? If you have two vectors, okay, let's say, let's do it this way. U and then V. All right? The way you can tell whether the orthogonal vector will point this way or this way, you can use your right hand to tell. So if I'm interested in U cross V, I know that vector, let me draw it a little closer over here, I know that vector is going to point this way. Because if I take my right hand, and I wrap my fingers, imagine wrapping your fingers around it so it goes through this first vector first, and then your fingers go through the second vector. Okay, so my fingers will go this way. Okay. And I have 4 fingers, so there we go. then your thumb points in the direction that the resultant vector is going to go. Okay? So if your fingers, let me write this down, the right-hand rule. If you curl the fingers of your right hand first through U, then through V, your thumb will point in the direction of U cross V, of the resultant vector from the cross product. So you curl your fingers through U, you curl your fingers through V, and then your thumb will be pointing in the direction of the resultant vector. All right? Notice if I swap them, if I want V cross U, then it'd be going the other way, and the right-hand rule helps me there too, right? Because if your fingers go first through, the fingers of your right hand go first through V, then through U, your thumb will be pointing down. Okay? Let's think about some of the properties of the cross product. Now, we do call it the cross product, so this is another vector operation that has a lot of similarities to multiplication. But there's one property, and we've already seen it, that is quite different from multiplication. Multiplication is commutative. 2 times 4 is the same as 4 times 2. I can switch things around without a problem. But the cross product is not commutative. It's anti-commutative. It's actually almost the opposite of commutative. Okay? U cross V and V cross U aren't the same thing. In fact, they'll be pointing exactly in opposite directions. And we saw that with the right-hand rule, right? If you curl your fingers first through U and then through V, your thumb will be pointing one direction. If you curl your fingers first through V and then through U, your thumb will be pointing the exact opposite direction. Okay? So this is a big difference from standard multiplication and also from the dot product, which also has commutativity. The cross product does not have commutativity. Order matters. Okay? But many of the other properties are similar to multiplication. It has a distributive property. So you can distribute, which also means, by the way, you'd be able to FOIL, right? If I had U plus V cross W plus Z, then you can do first, outer, inner, last, because foiling is just multiple distributions, applying that distributive property multiple times. Okay? So sometimes we might see that happen, where we need to distribute over a cross product. We also have associativity with scalar multiplication. Okay? Just like with the dot product, if I multiply by a scalar multiple, I can do the cross product first and then multiply by the scalar multiple, or I can multiply by the scalar multiple first, and it doesn't matter if I multiply the U, scalar multiply the U, or scalar multiply the V. Okay? Doesn't matter what order I do things in or where I put that scalar multiple. Cross product of the zero vector. It doesn't have the same geometric interpretation of being orthogonal to both vectors, because you can't really be orthogonal to the zero vector, right? It's not pointing anywhere. But you can still do the arithmetic. And if you take the cross product of any vector with the zero vector, then you just get the zero vector. Not surprising. Okay. This last one is maybe just a little bit surprising, though if you think about it, it's not that crazy. If you take a vector and you take the cross product of the vector with itself, you get 0. Okay. Remember that the idea of the cross product is you want a vector orthogonal to both vectors. Okay. Well, if you have a vector and you take the cross product with itself, then you only have one vector, and there are lots of vectors that would be orthogonal to that vector, to that one vector. And so rather than trying to pick one, it just pops out 0. Okay, there's just too many choices. It kind of overloads the arithmetic, so to speak. All right, so cross product of a vector with itself, you get 0. That also means that because you could take a scalar out, the cross product of any two vectors that are just scalar multiples of each other would also be 0. There's one other really important property about how we define cross products. So let's let U and V be vectors in 3 dimensions so that the cross product works. Remember, this cross product only naturally works in 3 dimensions. And let theta be the angle between U and V. Then we have this property that's going to feel very similar to a property we have with the dot product. Okay? If we take the cross product of U and V and then look at the norm of that cross product, this would be equal to the norm of the first vector times the norm of the second vector times sine of the angle between them. Okay, now remember that's very similar to the dot product. Dot product is almost the same. It's also norm of the first vector and norm of the second vector. But then instead of sine theta, it's cosine theta. So we're kind of getting the other side of the trig function. Okay, the other trig function here. So let's prove this. The proof at the beginning is a bit fiddly. So let's take a look here. We won't write it all out, but I want you to understand where things are coming from. Okay? So we're looking at the norm squared. Notice we decide to square the norm. That's common practice in a lot of proofs involving norms, because if you square it, then you don't have to deal with the square root, right? And so we look at the components of the cross product, and because it's in a norm, we square those components, and we add them together. All right? So far, so good. Okay? But if we want to do any kind of manipulation, we actually have to FOIL this out. Each one of these got to FOIL them out. Okay? So they do that, and that's what they get here. Right? Lots and lots of terms. What they do is they carefully manipulate the terms and move them side to side so they can get some very nice factoring. So by moving the terms around, you can end up with this factorization. Now this isn't obvious. You really have to stare at it for a while to convince yourself that this factors to this. Okay? But it does. But this is where it really gets useful. Okay? Because then this is just norm of u squared. This is the sum of the components of v, each squared. So that's norm of v squared. And then this, well, this looks familiar. We have u1 v1 plus u2 v2 plus u3 v3. That's u dot v. And then we just square it. Okay? Well, what do we know about u dot v? U dot v is norm of u times norm of v times cosine theta. And since it's squared, each one of those factors gets squared also. And now look, I have a common factor in both of these terms. They both have norm of u squared, norm of v squared. So let's factor that out. Usually factoring is a good strategy for any problem. So if you see something like that, factor it out. That leaves me with 1 minus cosine squared. Well, 1 minus cosine squared, well, that should ring bells. That should ring alarm bells, right? That is a very well-known trigonometric identity. 1 minus cosine squared is equal to sine squared. Okay? And we essentially have our answer. Norm of u cross v squared is equal to norm of u squared, norm of v squared times sine squared theta. We just have to take the square root now. Okay? Now, technically, you got to be a little careful when taking square roots. But in this case, we're all good. Norm of u and norm of v are positive, so when we take the square root, we really do just get norm of u and norm of v, right? Now, sine of theta doesn't always have to be positive. And if we have a negative number squared, the square root of a negative number squared doesn't have to give me that same number back, right? So square root of 2 squared, well, that's 2. Great, right? But square root of negative 2 squared, negative 2 squared is 4. Square root of 4 is 2, right? It doesn't just cancel the square. So we have to be careful. As long as we're plugging in positive numbers, it will spit out the same thing. But generally, the rule is that the square root of x squared is going to give you the absolute value of x. It spits out the positive version of x, all right? With norm of u and norm of v, those are positive. Those are lengths. We're good. We don't have to worry about that. But with sine of theta, sine could be negative, okay? But in this case, theta represents the angle between two vectors, okay? Represents this angle here between two vectors. What's the biggest that angle can be? Well, the absolute biggest is if they're pointing in opposite directions. Be 180 degrees or pi, right? If I go beyond that, if I stretch this a little bit beyond, now we don't measure it this way, we're measuring it this way again. We always take the smaller angle. So that's always what we mean by our theta, okay? So theta will always be between 0 and 180 degrees, and sine is always positive for theta between 0 and 180 degrees. So in this case, because sine is always positive, square root and square will cancel. We will just get sine of theta. Okay? And that gives me my final result here. Okay? So let's summarize. We learned in the previous section that if we take the dot product of two vectors, we get norm of u, norm of v, cosine of theta, where theta is the angle between them. In this section, we're now learning that if we take the cross product and take the norm of that cross product, we get norm of u, norm of v, sine of theta. Okay, so it gives us cosine of theta and sine of theta, the two most important trig functions with the angle between them, the angle that is being plugged into those trig functions. So we know now that the norm of the cross product is equal to the norm of u times the norm of v times sine of theta. What this means is that we can do something that's going to be useful later on in the course, okay? So imagine we have two vectors, u and v. Okay? And imagine we take these two vectors and we make the parallelogram determined by these two vectors. So that is, I'm going to draw you again here. So that's also u, right? Because vectors don't have a position. That has the same direction and magnitude as u. And then I'll draw another vector v right here. And so if I put that all together, I get a parallelogram. Now, later on in the course, it's going to be quite useful to know the area of this parallelogram. The area of any parallelogram determined by two vectors. Okay? We're going to need to do that once we get to integration. So let's think about the angle between these. We know that the area of the parallelogram is just the base of the parallelogram times the height of the parallelogram. Now the base is easy. I can choose vector v to be the base, and so I need the length of that base, which would be the norm of v. So I'll take the norm of v, that's the length of the base of the parallelogram, and then I need the height. For the height, I need it directly straight up from the base. I need to know how long is this, okay? Well, we know we want to make a right angle with this base, and so we have a right triangle, and we know the angle between them is theta, right? This angle here is theta, and so we can use a little trigonometry to find the length of this base, okay? We know that the height here, let me label it, the height here, if I take sine of theta, I get opposite, which is the height, over hypotenuse, which is the norm of u. Okay? And if I just move that norm of u over, then the height that I'm looking for is just norm of u times sine theta. Okay? That is what the height is equal to. It's norm of u sine theta. And so if I plug that in from my height here, get norm of u sine theta. And goodness gracious, this formula does look familiar, doesn't it? It's exactly this formula right here. So the area of a parallelogram determined by the vectors u and v is just the norm of the cross product of those vectors. And so it gives us a real easy way to find the area of a parallelogram if I can describe this two adjacent sides of that parallelogram as vectors. So let's take a look at this example. In this example, we have 3 points, A, B, and C, and we want to find the area of the parallelogram with adjacent sides, where one of the sides points from point A to point B, and one of the sides goes from point A to point C. Right? So notice first for this example, the problem isn't giving us the sides on their own. It gives us points and says we can find the sides from those points. All right? So let me draw kind of an illustration. We won't draw this perfectly because it's a complicated structure in three-dimensional space, but just so we can get the idea, we have 3 points, A, B, and C. Okay? And we want the area of the parallelogram with adjacent sides, AB and AC. So before we do anything, we need to find these sides, AB and AC. Okay? We're going to do this the way we usually do. I have a vector here. I can find the vector by using some subtraction, n minus start. Okay? So vector A that goes from A to B, I want it to end up at B, so I'm going to treat B as a vector with components 1, 1, negative 1. and then I'm going to subtract the vector that points at A, 0, 3, 2. Since that's where I want to start. I want to start at A. And so this first vector is 1, negative 2, negative 3. Okay, and then do the same thing to find AC. I want the vector that starts at point A and ends at point C, so I'm going to do n minus start. I want to end at point C, that's 2, negative 1, 0. I want to start at point A, that's 0, 3, 2. If I subtract, I get 2 minus 0 is 2. Negative 1 minus 3 is negative 4, and 0 minus 2 is negative 2. Okay? Now I know that the parallelogram determined by these points, I can find the area by taking the norm of the cross product of these two vectors. Okay? So let's take the cross product. So AB cross AC is going to give me, so I'm going to construct my matrix and then find the determinant. So first vector first, AB first, that's 1, negative 2, negative 3. And then AC second, I get 2, negative 4, negative 2. Okay? And I'm going to do this a little faster. Try to, in your mind, cancel out the row and column with I in it. Okay, so for I get 4 minus 12. 4 minus 12 is 8. Negative 8. So negative 8I. Then J, I get negative 2 minus negative 6. So negative 2 plus 6 is 4. And then finally for K, negative 4 minus negative 4 is 0. Alternate the signs, plus, minus, plus. My vector is negative 8, negative 4, 0. Okay? That's the cross product. But to find the area of the parallelogram, I want the norm of the cross product. So now the norm of this guy, norm of the cross product, I'm going to take the square root of the sum of the squares of the components. So first component squared plus second component squared plus third component squared. Negative 8 squared is 64. 4 squared is 16. I don't have to worry about the 0 squared. And so I get square root of 80. And that's technically your answer. If you want to simplify the root, 80 is 2 and 40, which is 2 and 20, which is 2 and 10, which is 2 and 5. And so I could pull out 1, I could pull out 2 2's, and I have a 5 that I can't pull out. So I have 2 square roots of 5, or 2 squared times the square root of 5, or 4 times the square root of 5. That is the area of the parallelogram with these two adjacent sides. Okay, so we can find the area of a parallelogram determined by two vectors using the cross product. That's pretty nifty. Can we go a step further? What if we get the three-dimensional equivalent of a parallelogram? So say we have 3 vectors instead of 2. So let's go vector U, vector V, and vector W. Okay? Now, let's put all these together to get like a three-dimensional parallelogram shape. So we get something like this. Okay? We call this shape a parallelepiped. Parallelepiped. Okay, it's the three-dimensional equivalent to a parallelogram. So instead of finding just the area of a parallelogram, can we find the volume of a parallelepiped determined by three vectors? Okay. Well, here we could find the volume by taking the area of the base. So not just the length of the base, but the area of the base. So all of this. Okay? And then multiplying it by the height. All right? Well, the area of the base of a parallelepiped is a parallelogram. It's a parallelogram determined by u and v. And we know how to find the area of a parallelogram. It's just going to be the norm of the cross product of those two vectors. Okay? Now what about the height? Okay? Let me draw the height over here. So we want to find out how far we need to go that high. All right? So we want this length here. It'd be really great if we could find a vector that points going directly away from the base, right? Because that's how we want to find our height. We want to go directly away from the base. That would mean we want to be orthogonal to both vector v and vector u. How could we find a vector that is orthogonal to both vector v and vector u? Well, how about taking the cross product? Okay, we could take the cross product, u cross v. That will give us a vector that points in the same direction as we want to measure the height. Right? Now, it won't give us the height itself, right? It may not be as tall as we want it to be, for example. All right? But what we want to do is we want to take vector w here, and we want to project it onto the line that this cross product is in, that this vector is in. We want to see how long is w in this direction. Now we know how to do that. That's orthogonal projection, right? Except we just want the component. We just want the length. We don't want the whole vector because we just want the height. The dot product tells us that the component of this in this direction. Okay, so remember the height here. If I want to know how much of w, the component of w in this direction, I'm going to take the dot product of w with the unit vector pointing in that direction. Okay, so the unit vector of that. So I'll take u cross v divided by the norm of u cross v. Okay, that turns the cross product here into a unit vector. And so by taking the dot product of a vector with a unit vector, it tells me what is the component of this vector in this direction. Okay, how much of vector w here is pointing in this direction. It will give me this height here. How much is that? Okay, so this is the height. And so that's essentially the formula, that we can tidy it up. Okay, this is just a scalar value. And if you remember, multiplying a scalar by a dot product, we have associativity. So I can multiply this by just w, or I can multiply this by just this, and I'll get what I want. So I'm going to actually move this in and multiply it by this. Okay, so I get w dotted with, going to get my scalar multiple, u cross v, times the vector u cross v over norm of u cross v. And you could see that this and this will cancel very nicely. And so my final formula here, the volume of a parallelepiped, would be W dot U cross V. Okay? And actually, I got to be a little careful here, because the way I've done it, the way I've written it, this component here of W will be positive, but it doesn't need to be. The dot product here doesn't need to be positive. Now we want a volume, a positive amount. So really, if I want to make this perfectly accurate, I should have absolute values here. Actually, that one was okay. I want the absolute value of that dot product. And so I end up with this. So the absolute values make sure we have a positive volume when we're all done. Okay? So this gives me the formula for the volume of a parallelepiped determined by vectors W, U, and V. Okay? Now I should say I've chose U and V to be the base and W to be the third vector. But I could have chosen any one of these vectors, any one of these surfaces to be the base, right? I could have chosen the surface determined by W and V, or the surface determined by W and U to be the base of the parallelepiped. So the order here doesn't matter. Okay? You could swap any of these, and as long as you have the absolute value bars, you'll get the same answer when you're all done. Okay? But this is going to give you the volume of a parallelepiped determined by vectors U, V, and W. So let's take a look at an example here. We want to find the volume of the parallelepiped with adjacent edges A made up with vector A, vector B, and vector C. Okay? So you could draw that out in 3 space if you want, but we will essentially have something that looks like this. A, we have 3 adjacent edges, B, C, and then just the parallelepiped that's made up of those. Let's see, more like that, yeah? Let's see, B small. Okay, we just want the volume of that parallelepiped. Now I totally made up what A, B, and C look like, just to be clear. But we know we want the volume of a parallelepiped with these 3 adjacent sides. Now we just derived the formula for the volume. You're going to take the dot product of one of these vectors with the cross product of the other 2. Okay. Now, which one goes where isn't important. As long as you throw them in an absolute value, you'll get the same answer when you're done. Okay? So, what would we need to do first? Well, we'd have to do the cross product first, right? That's the one in the parentheses. Okay? So let's find the cross product of vector B and vector C. Okay, so quick cross product, I, J, K, components of vector B, 2, -1, 2, and the components of vector C. If you were to distribute that 3, we'd get 3i plus 3j minus 3k, so we'd get 3, 3, -3. So take that cross product. For the first component with the I, I'd get 3 minus 6, so -3. So -3i, so that's our first component. Okay, in fact, let's be consistent. The rest of the problem is using I, j's, and k, so negative 3i. For j, I get negative 6 minus 6, so that's negative 12. Negative 12j. And then for k, 6 minus negative 3. So that's 9. 9k, make sure you alternate signs. Plus in front, minus in front, plus in front, right? So that means just a minus there, plus there. And I get negative 3i plus 12j, with a double negative there, plus 9k. Okay, that's b cross c, that's this guy. Okay, now I need to take the dot product of that with a. Okay, so let's plug that in. Vector a was I minus 3j minus 2k. I minus 3j minus 2k. Make sure I wrote that down right. Looks good. And I'm going to take the dot product of vector a here with the cross product of b cross c. B cross c is this right here. Negative 3i plus 12j plus 9k. It's all inside absolute values. Okay, so multiply corresponding components. So I get 1 times negative 3 is negative 3 plus negative 3 times 12 is negative 36 plus negative 2 times 9 is negative 18. And so I have negative 3 plus negative 36 plus negative 18. Oh, what is that? So I get negative 39, negative 49, negative 57. And it's inside absolute values, so it turns out negative 57 into a positive 57. That is the volume of the parallelepiped determined by these three vectors. Now I just want to wrap up this section with one final thought. I've spent a lot of time talking about how this really only works in 3 dimensions. This is a 3-dimensional operation, and that is true. But sometimes we could take something in, say, 2 dimensions and embed it into 3 dimensions, okay? And we would want to do this because if we have 2 vectors u and v in R2, say 1, 3, and maybe v is equal to 2, 7, these are 2-dimensional vectors. But there are things with these 2-dimensional vectors that we might want to do. The cross product is very useful for finding things like the sine of the angle between vectors, or helping us find the area of a parallelogram. These are things that we would want to do in 2 dimensions as well as in 3 dimensions, right? So how can we extend the idea of the cross product to 2 dimensions? So the trick is to embed the 2-dimensional structure, the 2-dimensional space, into 3 dimensions. I can think of 2-dimensional space as just the xy plane, and I've mislabeled the axes, haven't I? This should be the y-axis, this should be the z-axis. Okay, I could think about this as 2-dimensional space embedded in 3 dimensions. And if this plane is 2-dimensional space, then I can think about these vectors as not just 1, 3, but I can tack on a 3rd component where z is 0. I could think about v as 2, 7, and then tack on a 3rd component where z is 0. Okay? These behave just like they do in 2-dimensional space because they live in this xy plane. But they're 3-dimensional vectors. And so I can take the cross product of these. Okay? And so if I find the parallelogram, for example, Okay, so maybe I find a parallelogram with adjacent sides u and v in three-dimensional space. That parallelogram is still embedded in the xy plane. It's still a two-dimensional parallelogram. And so, but if I think about u and v as three-dimensional vectors, I could take the cross product of those three-dimensional vectors and find the area of the parallelogram. The area of the parallelogram in three-dimensional space is going to be the same as the area of the parallelogram in two-dimensional space because it's essentially the same parallelogram. Okay? It's embedded in this two-dimensional plane. So sometimes we're going to want to do that. The properties, some of these properties of the cross product are so useful that we will extend their ideas to two dimensions by just tacking on a third coordinate to our two-dimensional vectors. Easiest choice is 0. So we can tack on a 0 to those two-dimensional vectors, turn them into three-dimensional vectors, and that allows us to take the cross product of those two-dimensional vectors.